Dr. Bowser said a few years before that as well, that I've been working on. So a little bit about me for some of you that might not know as well. I'm from Hettinger, North Dakota. That's way down here in the southwest corner of North Dakota. And down there is kind of honey country. There's a ton of beekeepers, a ton of honey gets produced down there, up in this northwestern South Dakota part as well. And so I have a lot of family and friends, beekeepers, and so I've been working with bees now for 8 years. So this is me back in high school actually working at my uncle's honey company, and that's my friend Noye. And so this will be 8 years of working with honeybees, and throughout this whole process I've seen a lot of success, but I've seen all the hardships and the hard work and everything that comes along with that success. Particularly where I focus my efforts for my master's degree was on pollination services, particularly the transportation to said pollination services. So according to the FDA, about a third of our food comes from crops pollinated by honeybees. That's about 90 plus crops that rely on bee pollination. This includes apples, blueberries, melons, broccoli, and particularly almonds. About 80% of the world's almonds are produced in California, and that could not be possible without honeybees being sent there for the pollination services that they do. So there's a ton of different factors that lead to the decline of honeybees, and that's why this research is so important, because with this pollinator decline that we're seeing, something needs to be done. If we look at this graph by the Bee Informed Partnership, these are actually the survey years where they surveyed beekeepers to see what percentage of their colonies they're losing each year. So if we look at this as of 2019 to 20, we see that it's a little over 40% of the annual bees are lost per year in these surveys. So that means of a beekeeper's, all of their colonies, they are losing 40 out of 100 hives a year. And so how is this sustainable? The short answer and long answer are kind of different, and they both kind of amount to it's not really sustainable. But what they're doing right now to keep up is every year they're splitting all of their bees. They're taking bees from hives, they're raising new queens, and they're basically splitting one hive into 1, 2, 3, perhaps even 4 hives. And they're taking those bees and adding more queens to each of those hives. So they're losing 40% each year, but they're trying to regain as they can every year along with them. And the reasonings for this are quite a few. Disease, nutrition, pesticides, fungicides, particularly what I'm looking at in transportation. But all of these things do affect honeybees and their survival. Again, just another look at it. They've factored some of these into different categories, whether we're looking at quality of queens, diseases, parasites, pesticides, land use, and management practices. Specifically, where I'm looking at transportation, this is a decision by beekeepers to do it, so we're sitting in this category right here of how beekeepers are managing their bees. This is what honeybee colonies actually look like in California, where they're pollinating almonds. There are tons of bees here that they put just to go to every flower, pollinate the almonds. As you can see, that's quite a few bees, and so that's not particularly helpful, especially if you're trying to protect your bees from diseases, parasites, viruses that are transmissible between bees. They're also very close in contact, and it's not good for them. So here's a map of all the places that the big pollinator events that honeybees are transported to across the U.S. The big one right here is in February. That's the almond bloom that I discussed, where 80% of the world's almonds are grown. And so on that west coast, it's particularly stuff like almonds, apples, cherries. And then later on in the year, they get transported over to where we're at, North and South Dakota. And this is where they actually gorge out on all their honey production. So this is where they will make a lot of their honey reserves, and beekeepers will take off those honey reserves to sell for money. And then they can get transported also to this East Coast side up in here for blueberries, cranberries. Down south it can be stuff more like melons, zucchinis, and then on the East Coast they travel up and down, pollinating just a ton of crops on the East Coast. Yeah. So this is actually what transported honeybee colonies look like. As you can see, they strap them down, cover them in nets so the bees can't escape. Typically they transport them in cold temperatures or at night. This appears to be warm temperatures and day. It's really hard to visualize that if you're looking at a picture in the night, but yeah, as you can see why, there's a lot of bees escaping under this net. Ideally, yeah, you want to trap them in their hives and transport them when they're not going to be flying. So this research led me to two main research questions, based on kind of one overarching. So the overarching question is, does vibration affect honeybees? And so from this, I developed two questions. The first being, are there initial or prolonged effects of honeybee metabolic rate in response to vibration stress? And the second being, is the development of the gland that produces royal jelly in honeybees affected by vibration stress? So, for my project, I wanted to focus on mainly hives, and I'll touch on that in a second a little bit more. So I did the best I could to create a very replicable version of honeybee hives while still maintaining that same environment and structure of a hive. So I used these mini nuke colonies. These are little boxes that I put bees in right here. So this is the main area where the bees will actually stay, and then this is a feeder right here where I would provide food for the honeybees. And then I provided a queen mandibular pheromone strip on this frame right here. And what that it does is basically simulates a queen right colony. Queens can be very expensive and sometimes more difficult to keep maintained in a hive this size. So the best I could do was keep the workers like there was a simulated queen within the hive by giving off the pheromone that the queen actually emits. And so for my shaking, I use a vibrating offset motor, which I'll show you in a second, and an accelerometer to quantify that shaking compared to other truck studies. As for the queen pheromone strip, this is what they look like. And what these basically do, so if I ever say QMP, that's that queen mandibular pheromone that was put in the hive. So it primes the bees to perform colony-related tasks, it inhibits their ovary development, prevents attempts to rear a new queen, stimulates workers for care of a queen, influences comb-building activity. And it is super funny. It's kind of sad a little bit because the bees love this. They really do think it's their queen. They'll huddle around it, try to groom it, try to feed it. It is sad, but it's their queen. They love it. So previously, there was work on transportation, specifically with foods in the food industry. So one of the big ones I found research on is by this Shibazi et al. And it was basically, their premise was building a shaking simulator in a lab to simulate transportation. And they had watermelons, and they were trying to find out at what point of this shaking in trucks do the watermelons rub against each other and create damage to the fruit. So this is really the only study I found that actually had an in-lab simulation of a transportation stress. So this is what I kind of tried to compare my study to validate my travel. And so they had different frequencies and amplitudes, as did I. So frequencies is going to be how many times a wave travels up and down, basically in a second. So how many times that wave travels up and down. So for example, there's 7.5 hertz is in 1 second. That wave traveled up 7.5 different times. And then that amplitude is actually the measure of how high that wave goes. What is the impact of that wave? And that's measured in gravities. And so for their study, they used a high and low, basically transport, frequency and amplitude. And compared to mine, what I basically found, specifically my z-axis is what they looked at, because I have 3 different axes for this transport. You got your z-axis, your y-axis, and your x-axis. And so I had X and Y also, but they only had a Z. So for their Z-axis, they basically looked at a maximum of 15 hertz and a maximum of 0.75 Gs. So my motor runs at about 40 hertz, which is much faster up and downs of the wave, but my impact to these Gs, how powerful the shaking is actually very similar. All of them fell within the ranges they used for this study. Their bottom bound being 0.25 Gs and their upper bound being 0.75 Gs. Well, one of my axes was 0.25 Gs, and the other axis was 0.75 Gs. So, when looking at this, the impact of my shaking is very similar, but my frequency is much higher than theirs due to the nature of the motor. So, why use these mini colonies? So honeybees are a eusocial species. They live in hives, unlike other insects out there. And so there are behavioral differences at this hive level. So this should be considered when looking at things like metabolism. And so some good examples of this behavior and interaction among the hive would be winter cluster, as you can see right here. Not many insects actually produce a ton of heat like honeybees do. During the winter, they will use their honey stores to keep the hive at about 90 degrees Fahrenheit, even higher if they're raising brood. Nursing and grooming behaviors, they will clean each other, they will feed each other, they will do all of those things. And then, of course, defensive behaviors. Many of the hymenopterans that are eusocial have defensive behaviors at the hive level that they emit in times of stress. So, coming back to my questions, the first one I will be looking at is metabolic rate in honeybees. So I wanted to know if there were initial or prolonged effects on the honeybee metabolic rate in response to the vibration. The first thing here is, how do we use respirometry? Why do we use respirometry to measure metabolic rate? So, all living things on the planet use cellular respiration to produce their energy. Metabolism, animal energetics, they call those the fire of life. And so if we look at this equation right here, this is cellular respiration and the inputs of cellular respiration and what comes out after it's complete. So in this case, we're putting in glucose and oxygen to produce CO2, water, or carbon dioxide, water, and a ton of energy. And so with respirometry, you can either measure this oxygen input or the CO2 output. Or you can measure both if you wanted to. And so you're basically measuring the breathing of the organism because everything needs to do this to create energy. And so I am specifically looking at carbon dioxide. The main reason is because, to be quite honest, it's easier to detect. It was once explained to me like a bathtub, and bear with me here. So if you have a bathtub and you will say we're looking at oxygen, we'll say 20% of our atmosphere is oxygen, somewhere in there. And so you have a bathtub 20% full of blue marbles. If you take a handful of these marbles and you pull them out of this bathtub, you're probably not going to realize that any marbles were taken out of that bathtub. But with about, I think it's 0.04% of our atmosphere being CO2, you have a bathtub with 6 marbles in it, you're definitely going to notice if you throw a handful of marbles in that. So that is why I looked at CO2. It's very easy to detect the production of that. And they use this energy produced through cellular respiration to do anything. Locomotion, growth, reproduction, bodily and cell maintenance, brain reactions. Even making energy takes energy. So, looking at the setup for the respirometry equipment, I had the mini nukes that had my bees in them. I put them in this desiccator. It's an airtight little box with tubes running into it for airflow, electric inputs for the fan and the motor. The vibrating motor sits about right here. It's just in my, and you can't see it very well, but that's where it actually shakes that. And so this will actually impose like this, and then it's also inside an incubator that's modified. And that incubator is kept at 30 degrees Celsius to try to keep temperature stress out of the equation. The goal is to simulate as much as we could to a real honeybee hive, and so we didn't want them to be reacting to these cold temperatures, as especially worker honeybees are very susceptible to changes in their environment. So this is a wonderful graphic of my setup, and so how it basically works is we start off with an air compressor to run air all the way through this equipment. Most of it's air filters and scrubbing, making sure that air is completely clean of things like water and carbon dioxide, just making sure that when that air actually comes into this chamber, it is set at 0 carbon dioxide, 0 water, scrubbed of everything, so that when it comes out of this other side, when it travels through everything and comes out of this other side and feeds to my computer, that all I'm reading out of that air is what these bees are producing as far as carbon dioxide goes. And then so connected also to my computer is this shaking unit, which allows me to flip it on and off. It feels really cool having a lever to pull when you start shaking the bees. It makes you feel like you know what you're doing. So continuing on with my respirometry stuff, I had 58 mini new colonies. 27 of them were shaken and 31 of them were not shaken. And how I did this was I had them in the machine for about 2 hours. The first thing I did was take a machine baseline. That's basically flipping a switch and having the machine measure what is fully scrubbed air, absolute 0 from all the scrubbers straight through the machine. That is the 0 point for the machine. Then I took an organism baseline. So this was about a half hour of the bees sitting within the chamber, getting them used to it, acclimatizing to it. So you really see on the machine, you'll see that CO2 level just drop until they're at kind of resting flat line. And so that was what I measured to be the organism's base resting rate, because they're never not going to be producing carbon dioxide. So next, I shook them for 30 minutes. So that's me flipping the lever and them in this machine shaking for 30 minutes. And then I flip the stop switch. I let them rest for 50 more minutes, and then took another machine baseline again to make sure I had that level set at what the machine is. So what I did next was bin this into 10-minute intervals. It's a little confusing, but bear with me. So I took the 10 minutes of each of these intervals and separated them, binned them all out, and I took the average CO2 production for those 10 minutes, and I named them accordingly. It'll make more sense once I get to this next slide. So this is what I found right here. So each one of these, so base, shake 1, shake 2, shake 3, rest 1, 2, 3, 4, 5. Each one of those is 10 minutes of the respective interval. So S1 is the first 10 minutes of shaking average, S2 is the second 10 minutes, and so on and so forth. And so what do we see here? Really quite interesting. As soon as that shaker initiated, you would just absolutely see an incredible spike in that CO2 production. I expected to see that, but what was even more weird to me is I was still shaking them at this point and this point. So we'd see this huge initial shaking response in honeybees in their metabolic rates, and we see it immediately fall back down to here, shaking stops, and we see it fall down below the bees that weren't shaken. So the bees that weren't shaken, I did the same thing, put them in this equipment, but I never flipped that switch. So as you can see, they're quite flatlined here for the most part, but weird. So I ran an analysis on this, made a model for repeated measures, because these bees were basically measured 9 different times. So in order to account for that, I ran this model to account for time being a repeated factor. And so what I found first was this one And so I didn't find any difference, particularly looking at time or treatment. But what I found was this interaction between the shaking treatment and the baseline, where I started getting these significant p-values. So we're talking about comparing the shaken treatment to its own baseline, which is very significantly different, less than 0.0001. In fact, the test I ran didn't even have a 1, it was 0.0000. And so that very significantly different there, and you can see that very clearly from its own baseline, it's way higher. The next significant bin I had, no significant differences with shake 2, shake 3. These are both not significantly different from their baseline. But the next one I found was that when we start looking after the shake stops, we see a significant difference in this being way lower than its baseline of a p-value of 0.0192. And then even that next time interval compared to the baseline with 0.0327 p-value compared to its own baseline. So that was quite interesting. I have the rest of the p-values for that interaction right here. None of them were significantly different. Some came close, but not quite. So, additionally, moving forward, I looked at the entire intervals. So I looked at a similar model here, but instead of this time separating it into 10-minute bins, I separated into that baseline bin I talked about being their baseline, and then the whole 30-minute shake averaged, and then the whole 50-minute rest averaged. And on this one, when looking at just time and taking both of the treatments into account, I did see a significant difference in the time, or in the shake period, 0.0192, but not in the rest period. But when looking at, again, that interaction of the shake with its baseline, I had 0.0025 p-value and 0.0392 or 91 p-value for that, both being significantly different from its baseline, which is interesting. So, what did I find in this section? Nurse honeybee metabolic rate response to vibration is fast and strong. However, it is short-lived, it appears. So we see this fast initial response to the vibration, and then it quickly responds to baseline level, which makes me think, is it a startle? Is it like watching a scary movie and you see a jump scare and you freak out for a second, and then you're like, oh, it's okay now, return back to 0. If so, then why, when shaking ceases, do honeybees fall below that baseline? Are we seeing something like an exhaustion, like the shaking finally stops and they're like, oh, spend so much energy, it's so nice down here, they stop shaking? Or is it this requirement for uniformity in a hive? Does it not matter if you shake them or not, as long as you just keep doing it the same amount? If they're just constantly being shaken, they're okay with it. But once you stop, they just want this uniform environment. And then, because they return to baseline then 20 minutes after this kind of dip down below their baseline. So, addressing my next question, is the development of the gland that produces royal jelly in honeybees affected by vibration stress? So these glands are called hypopharyngeal glands. They are in the front of the head of honeybees, kind of right behind their eyes. They produce the protein fraction of worker and royal jelly. They're important for nurse honeybees at about 5 to 10 days old, and that is about the section that nurse honeybees are in their development. They reach their peak size and secretory capacity between that 5 and 10 days. So that's when they're going to be putting out the most royal jelly, feeding a ton of workers, queens, larvae, stuff like that. And what I found from previous research is that they're very sensitive to stress. Almost every paper I looked at involving stress in the hypopharyngeal gland, I looked, and it looked like they were significantly smaller in almost every study I looked at. And so those studies include things like nutrition, whether you're feeding honeybees extra pollen, they'll increase in size. If you're starving them with pollen, they'll decrease in size. When looking at parasites, the more varroa mites on a honeybee, the smaller their hypopharyngeal glands. Looking at pesticides, some of them show, well, most of them show smaller hypopharyngeal glands. But the other interesting thing is sometimes we see fewer of these little bulbs on them, or more of them, depending on the pesticide, and all things like that. And particularly, there is one study that looked at 3 different populations of bees and had them shipped to different places in the country. They looked at things like protein content, juvenile hormone, and then also the size of these hypopharyngeal glands. And the interesting thing that they found was that they really didn't find many differences, but across every single one of these sets of transported honeybees, they found significantly smaller hypopharyngeal glands. So that seemed like a good target for me to look at vibration. Is this vibration going to affect the size of these glands? So these are what the hypopharyngeal glands look like. Here's a drawing of them. It's a little easier to see, but these are actual hypopharyngeal glands in honeybees that from a picture that were taken. And so this is what they look like at that first day old, and then as they grow and mature, they start to fill up with this fluid, this royal jelly, and get to their maximum size and secretory capacity. Additionally here, the main thing that we're looking at is these acini, and these are the bulbs that come off the main duct or the collecting duct. So this duct here, I want to preface, is called many different things: the collecting duct, the main duct, or axial duct. If I say any of those words, that's what I mean. I'm going to try to stick with collecting duct, but if I misspeak, that is what I'm talking about. And so the thing that we actually measure is these acini right here that come off the collecting duct. So for this study, I captured emerging honeybees. So I basically had a frame that was full of capped brood, and I took it into the lab, put it into an incubator, made sure it was cleaned off. So the day when I came in, I knew all of those bees were less than a day old, because I had checked it the day before just to make sure that there were no bees on it. Then, after I captured those bees, picked them off the frames, put them in those little mini nukes, I waited for 4 days, and then I either shaked them or rested them for 8 hours at that 4 days old. So, in my little setup with a shaker, for the unshaken ones, I just put them in that thing, left them there for 8 hours. For the shaken one, I put them in that machine and left that shaker on for the entire 8 hours of that day. Then I waited 4 days, when they were 8 days of age, and I flash froze them for dissection. My numbers of them, I had 30 shaken bees with 10 acini each. I averaged the size of their acini, 30 unshaken bees. The only one that's different from this is I had a density measurement, I'll point that out in a bit, and that one had 27 shaken, 29 unshaken bees. So, continuing on, I dissected these glands according to Corby, Harrison, Snyder in 2018. So I basically snipped up their face plates and peeled it back, pulled their hypopharyngeal glands out, dyed them, took photos of them under a 10 times microscope. I Z-stacked them to produce these nice stacked pictures. And then I measured the acini using ImageJ, which is a measuring software, where I took a known error bar like this, and I can measure that error bar, and then I can measure all of the glands accordingly. So I measured the area, the shape, and the number of acini per micrometer of collecting duct. And so this photo is actually one I took. So this is not off the internet. This is kind of what my photos look like. Yes, so I have this, this is kind of the process of dissecting the head. So this is the dissecting microscope I used. Very small, very, very finite things to do. So I basically pinned them all through the eyes and the mouth. And then you snip down the sides of their eyes, cut this nerve ending right here, and you peel their face back. really makes you feel like a monster, but I got it done. And so you can actually see here this milky white that you can see right beside the eyes right here, those are the hypopharyngeal glands. So once you have that peeled back, you can just grab them with a tweezer, pull them out, put them in your fluid, and dye them. And so this is before I got my dye figured out. I realized I didn't have any pictures of my final bees. I just took pictures like, guys, look, this is really cool, at the time when I was trying to figure stuff out. So that's not how my dye actually looked under the microscope. That was in the process of me figuring out. And the reasoning for that is because if your dye is too dark, you can't really see the overlapping acini on each other. You can't see the edges of them. And if it's too light, you kind of have that same problem where there's no, I don't know what the word I'm looking for, comparison between the back plate and the glands. So it's hard to measure them that way too. So looking at what I found, the first thing I looked at was size. So when I did size, I'm actually drawing a circle really carefully around the edge of this, and then it basically spits out a value in micrometers squared. And so what I actually found in these bees was the shaken honeybees have larger hypopharyngeal glands than the unshaken honeybees, with a pretty significant p-value, less than 0.001. Quite interesting, as I definitely didn't expect to find that, considering every other study said that honeybees had significantly smaller hypopharyngeal glands when they are stressed. So that was odd. But my other measurements, such as shape, what I looked at here was I basically took the height of the hypopharyngeal glands divided by the width to get this metric. And we see they're kind of sitting around this 1.5, so they're slightly taller than they are wide. And so what I found was this. So the unshaken ones had smaller than shaken ones. And I was looking to see maybe they're more oblong, maybe they're longer, because these two things might have the same area, but they're different shapes. And that's particularly based around pesticide papers. Pesticides really mess up the shape of these glands, but mine were just smaller. I didn't see a difference in shape. And then the last thing I measured in these bees was the number of acini per length of the collecting duct. So for this measurement, I took a measure of how far I could get on this collecting duct, counted how many acini were there. Again, in this measure, I didn't see any significant difference. Some studies find that certain types of stress may lead to smaller acini, but greater abundance of acini. So that kind of motivated me to measure that here. So, to summarize, honeybee hypopharyngeal gland size increases, the shape does not change, and the number of acini per micrometer of axial duct or collecting duct does not change. What does that mean? Does that mean shaking is good? I mean, probably not. But we did see that hypopharyngeal glands were larger. Are we seeing a trigger for a new queen? Particularly this royal jelly is one of the main foods, one of the only foods fed to the queen honeybees. So I'm thinking maybe there is this stressful environment and we're trying to raise new queens so they can travel elsewhere to make new hives, as honeybees do. What I did find though was comparing two other papers, I found that my control looks like it's sitting at an unhealthy level, whereas my treatment, my shaken honeybees, are sitting at a more healthy level. Could this be because I did have a lack of brood? There are studies that show hypopharyngeal gland sizes are bigger when brood is present. And I'm going to touch on this a little more when I conclude here. So overall, what did I find? Is vibration stressful? So again, to recap, honeybees recover from shaking quite quickly and during consistent vibration, and then their metabolic drops below their baseline when vibration ends. Could this be an adaptation or evolution of honeybees since being transported for pollination services? Maybe. I think it's running on 3 decades that honeybees have been transported in very large numbers for pollination. So this makes me wonder, is this something that over these 3 decades we've seen so many generations of honeybees that they're just getting more used to it? Is the drop that we see after shaking an exhausted response? Is there a require for uniformity within the hive? Are we seeing that, would we see that if we transported honeybees for quite a while, would we see something that when we start and stop every time this truck is moving, is their metabolic rate raising and lowering at this time? If so, that could be quite an interesting study to do, see how many resources and energy they're using during a whole road trip where they're starting, stopping. Every time do they hit a pothole, that a pothole gets hit, is that metabolic rate increasing? And with hypopharyngeal glands, we see a positive effect regarding size, but again, the control are not at a healthy level. Is this because of lack of brood? Is this stress response to produce queens to leave a stressful environment? I'm going to touch a little bit more on some of those things in my future directions. So, let's start at the top. My study only looked at nurse honeybees. So that is honeybees that are about 5 to 10 days of age. And these honeybees actually aren't aggressive yet. So there would be some interesting implications for foragers. So forager honeybees are in the higher 20 days old, and that's when they're actually pollinating all these flowers. So if we look at hives with older workers, those are the ones that would have these more defensive members of the hive. Would we see a continuous, sustained aggression and metabolic rate of them trying to kill me for shaking their hive? And they stay angry for a while, so I'd be interested to see a study like that of how long they actually have an increased metabolic rate. Especially with flying metabolic rate, also in them trying to kill me, those are some of the highest metabolic rates that flying insects will see is actually when they're flying. Another future direction, as I kind of talked about, is what about an inconsistent vibration stress? What if we're starting the motor, stopping the motor, starting the motor, stopping the motor? Are we going to see over time a decrease in that startling effect, where they just get used to it? Or are they hitting that peak level every time? How much energy are they using? Another thing that I would be interested in looking at is juvenile hormone measurement. And so one of the big things I've seen recently is confinement stress, caging honeybees, which I did, is a real thing that affects juvenile hormone measurement, or juvenile hormone titers. And so I've seen that I read that when capturing them, those juvenile hormone measurements can change their job in the hive, so depending on these titers or what kind of job they have. And people have also seen them change size of hypopharyngeal glands. And so maybe with this brood, what we're seeing, or without brood, we might be seeing normal levels without brood of these hypopharyngeal glands. But with the confinement stress, they're shifted down even farther. And so a way we could do that is behavioral analysis and job determination in addition to these juvenile hormones. So looking at what the bees are actually doing in the hive, because researchers have found that with changing this juvenile hormone, you can revert a forager back to a nurse, and they will have larger hypopharyngeal glands, and you can accelerate a nurse into a forager, and she will start developing these hypopharyngeal glands, which is very interesting. And then lastly, another thing you can do with this is lifespan and reactive oxygen species analysis, seeing how long they live. There are studies that see higher numbers of reactive oxygen species in transported bees, as well as decreased lifespans. So with that, I'd like to thank everyone today for coming. Thank everyone in my committee, the USDA Insect Unit, the Boucher Lab, all my family and friends. And that any and everyone who helped out with any and everything throughout my 4 years working with bees here at MDS.